Hello and welcome. Today we are going to start our second chapter in this course of electrical measurements, and this chapter is going to be on ammeters, voltmeters and ohm meters. So, let us begin this talk with ammeters. Ammeters, as you all know, it measures current. And so far we have studied instruments like PMMC, electrodynamic, moving iron. So, PMMC, electrodynamic and moving iron So, these three types of instruments are inherently or in principle ammeters. Why I am saying so? Because you know that if we pass any current through the coil or the coils of these instruments, the pointer moves. So, the pointer responds directly to the current which is flowing through the coil or the coils of these instruments. So, these instruments are directly like ammeters. So, we can measure current with any of these instruments. Now, suppose if I have I can have a circuit which can be very complicated, but so let me take a circuit. You can think of a very complicated circuit. And say that I want to find the current in any of these branches, say in this branch, call it I. So, we want to find I equal to what? How much is this current? So, what do we have to do? We have to cut open this branch So, we have to open this branch and insert a meter here in series. So, this meter can be PMMC, this can or electrodynamic or AMI. So, this can be PMMC, can be electrodynamic or AMI in principle. Okay. So, the choice will also depend on the type of the circuit, maybe AC, DC, etc. So, right now let me just put a source without mentioning exactly what type of source it is. Okay. So, we have to insert this meter in this branch in series. Okay. So, the important thing to note or know about ammeters is that ammeters are inserted in series with the desired branch where we want to measure the current. Okay. Now, this is one important fact which I believe all of you know. The next thing which we should know is that so when we insert this ammeter in this branch, the impedance of this branch will change. So, this coil, the coil of this instrument has some resistance. So, the resistance of this branch will increase, and therefore, the current in this branch may decrease. Okay. So, when we insert an ammeter in any branch of an electrical circuit, the current in that branch may change or will always actually change slightly. So, will always change. So, this current in that branch may change from the value of the current before the insertion of the meter. Okay. So, this happens because of the resistance of the coil. So, this is due to the non-zero resistance of the coil of the meter. Okay. So, therefore, ideally what we would like to have is that the ammeter should have zero internal resistance, zero internal impedance. So, ideally we would like to have so, 0 is never possible. So, practically we should write very small internal impedance or resistance. Okay. So, this is the second fact about the ammeters. We would like the ammeters to have very low internal resistance or internal impedance. Okay. Now, let us take an example. So, let us take a small example. Suppose I have a circuit, very simple circuit, say a 10 volt source which has 8 ohm resistance in series and then some current is flowing in this branch. So, what will be this current? This current I will be equal to 10 volt divided by 8 ohm. This will be 1.25 ampere. Now, say I have an ammeter which has internal resistance of 2 ohm, okay, for example, and I want to measure this current. So, I am inserting the ammeter 2 ohm resistance. So, this is 8 ohm, this is 10 volt. Now, the current that will flow in this branch I, this will become 10 volt divided by 8 plus 2 ohm, which is 1 ampere, and this 1 ampere is not same as 1.25 ampere. So, therefore, we have a difference between the current that was actually flowing in the circuit and the current which is now flowing after the insertion of the meter. So, the meter will indicate one ampere. Okay. Whereas, if we are interested in the value of the current that was flowing actually in the original circuit, that was different. So, therefore, we have an error. Okay. So, the error in this case is quite large. Error is, therefore, we can write this as 1.25 minus 1 ampere. This is like 0.25 ampere, and this we call the absolute error. And if we want to measure, say, a relative error, and we can define it as the error divided by true value. We can also define it as error divided by the measured value, depending on the situation, into 100%. So, this will come out to be 0.25 divided by true current was 1.25. So, this is like 1 over 5. So, this is 20%, which is quite large in this case. So, ideally we would like to have the internal resistance of any ammeter very low. Okay. So, we want, once again, internal resistance of ammeters to be very low. So, this is quite obvious. Now, let us ask a more involved question, which is to say, how low is good enough? I mean, how low is low enough for an ammeter? Okay. So, how low should the internal resistance of an ammeter be? So, this is the question we are asking now, and the answer is actually right in front of us. Okay. So, we have seen a very simple circuit which is made up of a voltage source and an resistance in series. But if we had a complicated circuit, any complicated circuit, think of any complicated network. So, think of very complicated network, as complicated as you can think of. So, let me also put some current sources. And say then there is a branch in this circuit where we want to measure the current. Say we want to measure the current in this branch. Okay. So, now how low should the internal resistance of the ammeter be to measure the current in this branch? The answer lies in the fact that according to Norton's theorem, any complicated circuit can always be reduced in a simple circuit, looking from the perspective of this branch between so where we want to measure the current. So, using Norton's theorem, we can always find a simplified circuit, call these 2 points as A and B. So, we can always find a simplified circuit with one current source and some series and some parallel impedance or resistance in this case, call it R n, call this current source as I n, this is point A and this is point B, these two are connected joined by this branch which is a short circuit, okay, which is a zero resistance branch, and we want to measure the current in this branch. Okay. So, this is the general scenario always. Now, we will, so this is the equivalent circuit. And this is the impedance R n as seen from the perspective of these two terminals A and B as seen from this side. Okay. So, this is the internal resistance of this circuit R n, Norton's resistance. This is also same as Thevenin resistance. Okay. Now, we will put the ammeter there. Okay. So, this is the symbol of an ammeter. Okay. And this is terminal A, terminal B, this is R n, this is I n. Now, the question is, what will be the reading of this ammeter? Okay. Now, the reading of this ammeter will depend on the internal resistance of this ammeter. Say the internal resistance R I is the, or call it R A, is the internal resistance. Okay. Then the current that will flow through this ammeter, that will be the ammeter reading, it will be given by this I n, and then we can apply the current divider rule multiplied by R n divided by R n plus R A, where R n is the Norton's resistance or Thevenin resistance, both are same, you know. Of the circuit. Okay. And so, this will be the ammeter reading, but the true current that was flowing in this branch before the insertion of the ammeter, that was I n. So, this was the short circuit current. Okay. So, we can actually we often denote this as I short circuit, ISC. This is ISC because this is this short circuit current as seen from as terminal AB. Okay. So, the current before insertion of ammeter was ISC. So, now the ammeter reading, we want this to be close to ISC or same as ISC ideally, and that will be true only if, so ammeter reading will be So, ammeter reading will be close to ISC, that is the actual current that was flowing before the insertion of the meter when. So, ammeter reading will be close to ISC when this factor is close to 1. Now, when will this factor be close to 1? Only if R A is much less than R N. When R A is much less than R N, because then, so call this I A ammeter reading, then I A will be ISC multiplied by R N by R N. We can neglect R A because R A is much smaller than R N. So, this is approximately true, and this will be equal to ISC. So, this is the condition we want. So, we want the ammeter resistance to be much smaller than the internal resistance of the actual circuit as seen from these two terminals. So, that means the internal resistance of this circuit as seen from the terminal AB, that is R N, should be much higher than the ammeter internal resistance of the ammeter. Then only our reading will be close to the correct value. Okay. So, in our next video, we will talk about multi-range ammeters, and we will stop in this video here. Thank you.